Hello everyone and welcome back. This is my second video for CTP1. This video will be covering the temperature sensor part of the project and other components required for simulation. First of all, let's get started with the recap from the first video. I covered the background details of the greenhouse monitoring system and the important components that are required to be known before starting the project. Next, I had discussed the main aim of building this entire system and how it will be technologically sound and effective. I had also given an overview about the proposed approach I will be following to develop the system. Lastly, comparisons were made between the proposed approach and past research projects and the fact that my project is more stable and has more advantages than the past ones. As discussed in video 1, my IDE for simulating this system is Proteus. The Proteus software designs products which include both schematic capture and PCB layout modules. It is designed to be both easy to use and powerful. Engineers and technicians create schematics and electronic prints for manufacturing printed circuit boards for various projects. One of the other IDEs I will be using is Arduino IDE. As discussed earlier, Arduino is a very effective and user-friendly IDE. It is also compatible with all platforms such as Windows, Mac, and Linux. With regards to my project, the code is written on Arduino IDE and it will be converted into a hex file which is uploaded to Proteus IDE, and the system works based on the coding performed. I have decided I will first be making the individual simulations of each sensor and then will be combining them together in the end. This will ensure that each component works without any sorts of construction or coding errors, which is why I will be using Arduino Uno in the beginning phases and towards the end will be combining everything into Arduino Mega. The other components which I will be using are LM35 temperature sensor, DHT22 humidity sensor, LEDs, fan, motors, LDR, variable resistor, terminal, LCD, L293D driver. Temperature sensor LM35. LM35 is a basic temperature sensor that can be used for experimental purposes. It gives the output readings in degrees Celsius because its output voltage is linearly proportional to the temperature. The operating voltage range of this LM35 ranges from minus 55 degrees Celsius to plus 150 degrees Celsius, and it has low self-heating. The following are the applications of LM35 temperature sensor. First, it can measure the temperature of any medium and HVAC applications. It provides thermal cutoff resulting in the voltage going down to zero. Third, apart from measuring environmental temperatures, it also measures surface temperatures, for example, of a car battery. The circuit shown is for simulation of the temperature component. LM35 sensor is used to obtain the temperature of the plants in the greenhouse. When temperature exceeds defined level or critical level, the system automatically turns on the fan on high speed. When the temperature reaches the normal range, the fan slows down and continues to rotate at medium speed. Lastly, when the temperature drops down below the defined level, the fan turns off and the heating lamp turns on. Throughout this whole process, an alert of the live data is sent to the owner or the operator containing the data of all parameters. The servo motor controls the window flaps to keep the temperature intact. The window being full open, half open, and completely closed depends on the readings from the temperature sensor and the range they lie in. The LCD is used to view the data locally. It displays the temperature value of the LM35 sensor. I have used LN293D motor driver to drive the fan, which works according to the conditions discussed earlier. I have further used a relay circuit with a sinusoidal voltage source model and a lamp which turns on and off when temperature values vary. The relay circuit is used to provide isolation between low voltage circuitry and high voltage circuitry. Arduino is used to provide a control signal wherever the temperature changes. The control signal is generated from pins 9, 10 and 13. Now I will be showing the real-time simulation of my temperature sensor circuit. This is the simulation, the screenshot of which was shown on the previous slide. This is the temperature sensor, the readings from which are displayed on the LCD screen. The fan is currently moving on high speed, the lamp is turned off, and the servo motor is positioned in such a way that the flaps are fully open. Now, when I decrease the temperature and bring it to a medium range, the speed of the fan slows down. Now, when I decrease the temperature furthermore and bring it to a very low range, the speed of the fan decreases. The lamp is turned on, and the user at the other end can see the readings. It can also be seen that the servo motor has changed its position to turn the flaps completely off. This is the code for my temperature sensor. Now, coming back to the presentation, in the next video, I will be covering the type of humidity and soil moisture sensor used. I will also successfully complete the simulation and working of humidity and soil moisture sensor. These are the references I have used for this part of the project. Thank you for watching my video.